Hello and welcome back to Machine Learning. I'm Javita Christie, and in this video, we are going to talk about how you can evaluate regression and clustering models. If you want to learn how to evaluate classification models in machine learning, you can watch the previous video where I have explained different ways to evaluate a classification model. In this video, we are going to see how you can evaluate regression and clustering machine learning models. Remember that regression is a supervised model, but clustering is an unsupervised model. So let's begin. First of all, how do you evaluate regression? So we know that regression, a simple linear regression, can be shown through this line, which is y is equal to alpha plus beta x. Okay, here we know that x is the independent variable which is used to predict the value of y, which is the dependent variable. And we also have alpha and beta, where alpha and beta, where alpha is the slope, alpha is the y-intercept and beta is the slope. So these are the things that we require. And if you plot this line in a graph, in an x versus y graph, you will notice that it will create a straight line that's moving upwards, not always upwards, but a straight line always, because it's a linear regression. So in this case, you can notice that all these crosses that we see, okay, those are the actual data points, but all the circles are the data points that our model is predicting. So basically what we are trying to say for this particular data point is that for this data point, for this value of x, this should be the value of y. But in reality, for this particular data point, for this value of x, the value of y is actually this. So there is this difference between this circle and the cross mark that you can see. And that difference tells you how much error is present in your model. So for a certain value of x, say x cap, the value of y is predicted as y cap, whereas the actual value of y is capital Y. Okay. So the distance between the actual value of y and the fitted or the predicted value of y, which is y cap, that is known as residual. Okay. And the regression model can be considered to be fitted well if the difference between the actual and the predicted value, which is the residual value, is less. So if you take all the residual values and you find that that is very less, then your regression model is considered to be fitted well. But if the residual value is more, you can see that the regression line is not properly fitted. Now, R-squared is another measure in which you can measure whether your regression model is doing well or not. So this R-squared is sometimes also called the coefficient of determination if you are using simple linear regression. But if you have a multiple regression where you have multiple x variables that are used to predict one y variable, so you have many independent variables, then in that case, R-squared is also called the coefficient of multiple determination. Now, what can be the value of R-squared? It can lie between 0 to 1. In percentage, it would lie between 0% and 100%. If it has a higher value, that means your fit is better. That means your regression model is doing better. So how do you calculate R-squared? You can calculate it like this. R-squared is equal to SST minus SSE upon SST. Now, what is SST? What is SSE? I'm going to tell you that in a minute. So let's first talk about SST. SST is sum of squares total, which is equal to squared differences of each observation from the overall mean. Okay. So it's basically just taking the average of all the observations and then taking a difference of all the values from the overall mean, from that average, and then taking a square of all those values and adding them That is your sum of squares total. So the formula is fairly simple. It is yi minus bar y. Bar y is the average. Yi is each observation. That's why there is I, because it goes from 1 to n. And you take a square of all these values and add them together. Take a sum of that. That is the sum of squares total, SST. Now let's talk about SSE. SSE is sum of squared errors, which is simply the sum of the squared residuals. Okay, so what is residuals? We talked about that previously. Yi is the actual value of y, but y cap is the predicted value. So just take a difference of those two, square that, and take a total of all the residual values. That would be SSE. Okay, so you just have to simply put all those formulas, replace them in the R squared formula, and you can calculate R squared. Okay. Now let's talk about evaluating clustering. So remember that clustering is an unsupervised machine learning algorithm. All clustering algorithms are unsupervised machine learning algorithms. And to evaluate it, we have two methods, internal and external. We will first talk about the internal method. Here the cluster is assessed on the based on the underlying data that was clustered. Okay, and so what they do, they generally measure cluster quality based on homogeneity of data belonging to the same cluster and heterogeneity of data belonging to different clusters. Okay, so homogeneity means similarity. So when the data belongs to the same cluster, how similar is that data? And heterogeneity is the opposite, dissimilarity. So when data belongs to two different clusters, how different is that data? So based on this similarity and dissimilarity, you can evaluate whether the clustering algorithm is performing well or not. Okay. Now, how do you decide homogeneity or heterogeneity? It is decided based on some similarity measure. So, for example, one such measure is the silhouette coefficient, which is a very popular internal evaluation method. And what it uses is the Euclidean or Manhattan distances. And I'm sure we are very familiar with the Euclidean distance because we used that in our clustering algorithms. We used it even in KNN algorithm. So it's very fairly simple to use. So silhouette coefficient is something that uses that. Okay. Now what can be the value of silhouette? It can lie, the value of silhouette width ranges between -1 and +1. And if you have a high value, it indicates a high intra-cluster homogeneity. Okay. And intercluster heterogeneity. So if you have a high value of silhouette width, it would indicate a high intra-cluster homogeneity, which means between one cluster and another cluster, there is more similarity than there should be. And intercluster heterogeneity, which means between the clusters, there is some dissimilarity. So for a data set that is clustered into k different clusters, okay, so k is the number of clusters. How can you calculate the silhouette width? So you can calculate it like this. The silhouette width is equal to bi minus ai upon maximum of ai and bi. And here, what are bi and ai? So ai is the average distance between the ith data instance and all other data instances belonging to the same cluster. So consider A as one cluster. Okay. So you're just calculating the average distance between the ith data instance, and you can say the ith data instance might be the centroid of that cluster. So calculating the distances of all the points in that cluster from the centroid. Okay, and bi is the lowest average distance between the ith data instance and the data instances of all other clusters. So bi is measuring the distance of the ith data instance between one cluster and a cluster outside. Okay, So AI is about internal distance, BI is about distance of that cluster from the other clusters. Now consider this diagram. There are 4 clusters. Okay, this is the first cluster. This is cluster 2 right here. This is cluster 3. And this area is cluster 4. Okay, so what is AI, right? So you can see A1 is the distance. This is your centroid. Okay, so you're measuring A, which is the average of the distances of all these points that are in cluster 1 from the centroid. So A1 would be distance of this particular point from the centroid. A2 will be distance of this particular point from the centroid, and so on for all the points, and then take an average of that. That is AI. We also have BI. So what is BI? BI is the distance of the points in, it's the lowest distance, which means you'll just check that for this centroid, other than cluster 1, which is another cluster that is the closest. So you'll notice that cluster 4 is the closest out of the other 3 clusters, 2, 3, and 4. So you can measure the distances of all the points of cluster 4 from this centroid and take an average of that. So that is what will help you to calculate the silhouette width, right? So we know there are 4 clusters. Let's consider this arbitrary ice element in the cluster 1. So we know that AI is the average distance from this ice element of all the points in cluster 1. Okay, so it's simply all the distances divided by total number of points and 1. And same way, what is BI? So BI is going to be all the distances from that particular point divided by whatever is there in cluster 4. How many points are there in cluster 4? Okay. And here, of course, N4 is total number of elements in cluster 4. And we can, in the same way, calculate B13. Okay, we can calculate B12 and then take the minimum of all these values. So we can say that BI is the minimum of B12 average, B13 average, B14 average, like that. Okay. So that is how you can calculate the silhouette width. Now, what about external evaluation? This was internal evaluation. You can also do external evaluation where the class label is known for the data set subjected to clustering. Okay, but the known class labels are not part of the data used for clustering. So even though it is unsupervised learning, you still know the class label beforehand. Now the cluster algorithm is assessed on the basis of how close the results are to the actual class labels. Okay. So for example, one such measure for external evaluation is purity. It evaluates the extent to which the clusters contain a single class. So for a data set that has n different instances and c known class labels, and let's say that your algorithm generates k clusters, you can measure purity like this, which is 1 upon n into sigma k, k is number of clusters, maximum of k intersection c. So you're calculating the extent to which clusters contain a single class. So this is the value of purity. And this is how you can evaluate clustering. And we also told you how to evaluate regression. So out of all the evaluation methods that we have seen so far, for classification, for regression, and for clustering, from those, the methods which are given for regression, which is, the mean squared error and the R2 score, those we have already applied in one of our previous videos when we implemented multiple linear regression. But just for the sake of revision, I'll just repeat it over here. So this is the program we did at the time for multiple linear regression. And we imported all these libraries and functions. So we have pandas, we have sklearn.model selection to get our train test split function. We have sklearn.metrics to get our mean squared error and our R2 score functions. Both of these are going to help us to calculate or rather evaluate our linear model. And to implement our linear model, we are using the linear model class from sklearn. So this is the data set. The data set contains, it is the auto MPG data set, which contains details about different cars, their miles per gallon, number of cylinders, displacement, horsepower, weight, acceleration, the model year, and the origin. So this is our data set, and by now you hopefully know how to open a CSV file in Python using pandas and then print the first 5 rows using .head function. And if you want to take a look at the data types of all these columns, you could just do data.d types. And before we begin, there are some null values here. That means NaN values. NaN values are sort of null values or values that do not exist. And so we call them not a number. So that's why they are called NaN. So if you want to remove all those values, you could just write down data equal to data.drop_na function and pass in it these two parameters. One is axis equal to 0, which means you want to remove from the rows. And because you want to remove all the rows where such NaN values are there, you can do this kind of a thing. Of course, I have shown you how to handle outliers and null values. This is one of the methods that you could just remove such rows containing null values or outliers. Okay. Next, we are going to separate our data set into predictors and target. Target can be only one, but the predictors can be many. These are the variables or attributes of our data set that are going to predict the target value. So the target is the zeros column, which in our case is going to be the MPG column, and which is given here. So this is the MPG column. And 1, 2, 4, and 5. So 1, 2, 4, and 5 means cylinders, displacement. 4 and 5 are weight and acceleration. These 4 columns are going to be used to predict MPG. So cylinders, displacement, weight, and acceleration are the features or attributes which will predict MPG. So we have separated those two using the iloc function. Next, we are going to run our train, test, and split function so that we can split our data set into training and testing. And remember that this function returns to you the predictors train and predictors test as the first 2 parameters, and then the target train and target test, so as the next 2 parameters. And in the function itself, you will pass the predictors and the target, and you will be passing what test size you want. So 0.3 means you want 30% data for testing, 70% for training, and the random state number given is 123, which means it will start generating, start picking rows randomly from the 123rd row. Okay, so we're all set. This is just a quick revision, so I'm going a little bit faster since I've already covered this in one of the previous videos. Once your data is split, you are going to create your linear regression model by using the linear model class that we got. And linear regression is what we want to implement. So we have created an object of it called LM. And on LM, we are going to fit the training data. So that means the predictors underscore train and target underscore train. Whatever training is done, all that is stored into a model called model. So this is our variable model. And this then can be used to make predictions. So now that we have trained our data, we can test our data using predictors underscore test and see if the target test values that we are getting are matching with the original target values. So you have to write model.predict and pass the predictors underscore test into it. Whatever is generated is stored in prediction. You could even print it out and see what it is. Now, once we have our prediction ready, we can indeed calculate our two-score and mean squared errors both together, which I just explained. You can calculate that with just one line of code. If you want the mean squared error, you just have to write mean underscore squared underscore error, and you need to pass target underscore test and prediction. So these two things you are going to pass. Prediction is what your model generated, target test are the actual values, and it will give you the mean squared error. And if you want the R2 score, then again, you just have to call the R2 underscore score function and pass into it the actual values and the predicted values, and you'll get your R2 score. So it's as simple as that. For the other evaluation techniques for clustering, I'm going to do in the next video. So I'll see you there, and thank you for watching.